Wind mitigation device team. I have Marcos, I have Joel, and I have Junior with me. Our advisors, Dr. Tremonti and Javier Palencia. Let's jump right into it. This is our problem statement. There is a need, first of all, for innovative engineering solutions to mitigate the damage and destruction caused by hurricanes. Also, post-hurricane power outages are a major concern. And there is a need for clean energy generation using renewable resources. Now, I want to direct your attention to this couple of pictures we have here. As you can see, house damage usually starts by roof failure. And why is that? If you look at this picture, this couple of arrows here represent the wind striking the house at a 90-degree angle. And you can see how these vortices are formed on the roof. Same here when we have the wind striking the house at an angle, how these conical vortices are being formed. If you look at this bottom left picture here, this blue area, especially the one on top of the roof, represents very negative pressure or a vacuum. Now this happens when there's flow separation within the boundary layer, and that happens when we have high-speed winds flowing over such a surface. Now with all that in mind, we arrived to our objectives for this project. We wanted to design a device that would modify the boundary layer, that would reduce the pressure difference over a roof, and it would extract power from the wind while doing so. Now before we go into any details, I want to show you real quick our timeline. We can come back to it, of course, if you want to. Now I want to talk a little bit about the global impact that this project has. First of all, from the environmental point of view, we are generating green energy, which is great, of course, for the planet. From the global point of view, this device can be implemented in many, many different countries around the world. From the economic point of view, we are reducing the cost of electricity by generating clean energy from a renewable and free source, which is wind. And of course, and the most important impact is the potential that this device has to save a life. Now, another program that received our special attention because of its importance to a clean planet is LEAD. The Leadership in Energy and Environmental Design is a non-profit organization that focuses on environmental consciousness. Now, to give you an idea how important this is, nowadays all government buildings strive, they want to be LEED certified. And we mention this because our project qualifies for 2 credits. First, on-site renewable energy, and secondly, innovation in design. And since we're talking about innovation and design, we wanted to emphasize that this project is a completely new approach to wind mitigation. There have been some passive mitigation devices implemented in the past, as you can see in this couple of pictures here. However, this project is a completely new approach in which we use a dynamic device to not only mitigate the wind, but generate electricity while doing so. Now with all that in mind, I'll give you Joel, who will explain a little bit more about our project.
Thank you, Marcos. So the pictures that you see here conform the flow chart that we followed to complete our design study. But before going into any details, we started by doing a sensitivity study to eliminate some of the design variables that we had. The sensitivity study, we did it using ANSYS fluid. It's a widely used CFD software, and it's the most effective, most accurate fluid mechanics software that was available to us. So we decided to use it, and we create this geometry to do the entire sensitivity study. The geometry is divided into 3 zones. First zone is the outer flow, basically. We have the inlet in this side, the outlet at the right. Then we have a second zone, which is an area of interest, which is going to represent, is to calculate the flow around the house. This will be the house. And then we have a third zone, which is basically a rotating mesh zone to try to simulate the rotating flow around the turbine and how this is going to affect the entire study. Now, we divided this sensitivity study into 3 parts, being the first part, the mesh study. These are some of the meshes that we create. These are the pressure profile corresponding to those meshes. We were comparing those pressure profiles in order to determine which one were given the best results, and therefore improvement on mesh. This was our final mesh, and as you can see, it's a little bit complicated. What we got from there, what we learned from this mesh study is that the element size around the turbine needs to be at least as thin as the thickness of the blade. Then the triangular method is by far more accurate in order to use with turbulent flow, and that over the roof, which is the area of study, the pressure that we needed to calculate to obtain a good pressure profile over the roof, we needed to have a 1/10 a mesh size of 1/10 of the thickness of the boundary layer at 5 millimeters from the edge of the roof. So we calculated that thickness, and based on that, we should select a mesh size of 1/10 that thickness to get better results. Now Junior is going to explain the next two steps in the sensitivity study.
Thank you, Joel. Before I start with the next step for the sensitivity study, we gotta mention that we got two major constraints due to the wind tunnel that we use for experimental test. Number one was the wind speed. We were limited between 0 and 11 meters per second. Number two was the cross-sectional area, which we used 12% to scale all of our models. What you can see here is finding the best number of blades, and we started between 3, 5, or 7 blades for a straight turbine. First of all, I want to mention that we make a relationship between length of the turbine and tip-to-tip distance. In order to do that, this graph here represents all the tests and the trials that we went through in order to finalize with our proposed design in this case. I want to direct your attention to this blue curve. This represents the house by itself. The pressure profile on the house, not device on the front. All of this curve represents all other configuration that we use in order to determine which one was the best. And from this we learned that the 3-blade case 1, meaning same tip-to-tip distance, same length, was the best configuration to further the study. The next step on the sensitivity study was where to place the turbine. Okay, so what we did, we created a coordinate system between X and Y position. We made Y 0, meaning the turbine is going to be at the same level of the house. And then we start placing different positions within the X-axis. And from there we conclude that 0.015 meters gave us the best wind mitigation, the best pressure profile along the roof of the house. With that being said, we predicted before to put it at the same level of the house, and then we did the same study here, and all you see here is just pressure profile with all the different positions that we moved on the Y-axis, and we got that the best position for the sake of the argument, which is mitigate wind, was 0 meter on the Y-axis, so we got the same level turbine and house. Once this was performed, we step up to move for the experimental analysis. And really quick, I want to walk you through this. This is a 3D printing technology we use to print all our models and our models there. This is the wind tunnel cross-sectional area. I want to direct your attention to the wind turbine, which is right there. And then this is the house. Very important. The house was designed in a way that we can actually get the pressure reading, okay, in the center. Why in the center? Because we consider this symmetrical. If we can predict what's going to happen in the middle, we can relate that towards the whole house. From there, those pressure hoses were connected to a data acquisition unit. We use a caliper to properly place the distance between the turbine and the house. And also we use a tachometer to measure angular speed. And the wind pitot tube was just to calculate the speed that we were dealing with. I want to show you really quick a short video of experimental test. You see how the turbine starts rotating right there. The house, we're getting the readings from here. Now you will see my fellow student, working on getting RPMs from the model. And that's why you see you're already trying to get the RPM for different angles. And then same procedure, we follow the same procedure. Now Joel will explain in detail the analytical part of the study.
Thank you, Junior. What you see here is a transient video with the type of analysis we use. The only difference is you saw first the static pressure, now the velocity. The only difference, this type of analysis, the transient analysis, with the one we use for comparison is we use a steady state for a complete result. Transient will give us like as a progression, and we use it mainly so we can understand the type of analysis. Everyone here can understand the type of analysis we were running with ANSYS to obtain this exactly. The pressure profile on the roof, which we then extract in form of a graph and then plot it together with the points of pressure that we measure on the lab, and then create some graph of comparison that you're gonna see on the next slide. Now, it's important to mention that all the values of the boundary layer conditions, I'm talking about velocity inlet, the all dimensions from the cross section, the RPM of the turbine that we measured, those were put into ANSYS. as input into ANSYS, so we can replicate the same and compare the results. As you can see in this graph, the red curve corresponds to the experiment, the blue to the simulation. There is a small gap that we will discuss later on, but both profiles follow the same. Both curves follow the same pressure profile over the roof. So basically, we can predict what is happening on the real life situation, and that's gonna allow us to do a deep analysis of this new type of device. Then we try with the 3 straight blades turbine. As you can see, we are correlating our results. And what we found here is a counterclockwise rotation. However, this counterclockwise rotation generates a smaller pressure all along the roof, and that's the opposite of the effect we want to create. Therefore, we try with 3 blades twisted, and what we found is the same counterclockwise rotation, the smaller pressure on the roof equal, but we noticed that the angular speed of the turbine was considerably or higher than the straight turbine. Therefore, we decided to keep that angular twist for the rest of the turbines that we measured. You can see in the table. And then we tried with a twisted 2-blade harmonious because we needed that clockwise rotation. We got it from the experiment, but we noticed that it required a higher fluid velocity to begin the movement. Since the fluid is redirecting over the house, at some point is at slow velocities, the flow over the turbine and below the turbine compensates, and it acts almost like an airflow. It stays static until the velocity is really high, but that goes against the power generation we want to create. So we try with 3 and 4 blades. This is the comparison of the results, and now Marcus is going to explain in more detail the analysis we said.
Thank you. As you might have noticed, there is a little bit of a gap between the red curve, which is the data obtained from experiment, and the blue curve, which is from simulation. Of course, there are many reasons for which this could have happened, but we believe that one of the main reasons is because all the simulations were performed in a 2-dimensional configuration as compared to experiments. However, it is important to note that for the purpose of this project, the similar profile that these 2 curves have is far more significant than that small gap. So when we put everything together, this is what we obtain. And before I walk you through this graph, I just want to mention quickly that even though everything you have been seeing so far is at 10 meters per second, we also run a full study at 8 meters per second, and we obtain similar results. But since both are similar, we just show in 10 meters per second in all the graphs. So if you look at this graph here at the bottom, this orange curve that goes all the way down, that is a curve corresponding to the house by itself. These are all experimental data. And all the other curves represent when we put all those devices that you can see there in front of the house. As you can see, all of the devices are mitigating the wind. They're smoothing out that profile on top of the roof. And if you look at here, at this chart, we are enclosing these 2 numbers in red. The one at the bottom, 159 Pascal, that is the pressure difference for the house alone. And that is the pressure difference between the highest and lowest point on that curve. And this 27 Pascal is the pressure difference for the 3-blade Savonius turbine. Now, why do we point that one out? Because that would be our chosen design. That would be the best design among all those that we analyzed. And why did we choose that one? First of all, it has about an 83% improvement on the pressure difference on the roof. Secondly, it has a very high angular velocity, which is great for power generation. And thirdly, it's cost effective when compared to the 4-blade Savonius. Now, why do we compare it to the 4-blade? Because the 4-blade performed a little bit better when it comes to wind mitigation. However, its rotational speed was considerably smaller than the 3-blade, and that is not good when it comes to power generation. So for that reason, after an overall assessment, our proposed design is the 3-blade Savonius. Now, up to this point, everything we did was a small scale using those models in the lab. So at this point, we wanted to take all that data, all those results, and somehow try to estimate what will happen with the real size prototype in terms of power generation. And for that, we performed a dimensional analysis that Junior will now explain.
Thank you, Marcus. As a good engineers, we try to predict what will happen on the prototype, real scale. So the first thing we did, we got some constant, some assumptions, such as we keep constant the temperature, wind speed, and also density and viscosity, and also local speed of the sound in the case of the back moment. With that being said, we got a relationship. We start our dimensional analysis using Reynolds number. Reynolds number relates inertial to viscous forces. And what you see here is a relationship between model and prototype that didn't help our analysis because we're trying to predict the RPMs for the real turbine. Therefore, we move forward and we use the Mach number, which is a dimensional number, which is the ratio between the velocity moving through a fluid, an object moving through a fluid, to local speed of sound. And then we got a relationship here. That is a linear relationship between the model and the prototype. And then from there we can predict what will be the angular speed of the prototype. In the next slide I will show you this over here refers to the experimental angular speed that we got for all of the models. And on the right you can see the estimation, the calculation using dimensional analysis for the turbine. And then here our intent was to calculate, find out how much power and how much torque we can get from that. And as you can see here, we did it for different speed, and we got all those results that we will explain that later. Now Marcos will, with this in mind, Marcos will explain the next step of the story, which is electrical cell.
Thank you, Junior. As Junior was mentioning, once we have torque and power available, we can somehow determine how we want to connect this device to the house. And we have just three choices here. The first one, let's say, if we live in an area in which the wind comes and goes intermittent, then what we can do is connect that device to a DC generator and to a battery bank, so that every time that we have wind available, we can store that energy in that battery bank and eventually connect it to the house and use it. If we have small winds, but it's steady, what we can do is connect that DC generator directly to an AC inverter and directly to the house and use it throughout the day. Now, if we live in an area in which we have abundant wind throughout the entire day, throughout the year, then we can use this configuration, which we're using a dual meter. The dual meter, basically what it does is allows current to flow in both directions. So in the case that we have more energy than the house is consuming, we can basically sell that energy back to the electric company. And to finalize, we did a last analysis, which is a cost analysis. We divided it into three. The first one is about our very first model. You can see it over there in the table. That's the very first model we used to somehow prove this new concept. And including all the parts, we paid about $140. Secondly, we have a cost analysis from all the experimental parts and equipment, including a 3D printer from MakerBot, and everything comes to about $2,200. And finally, we wanted to do a very rough estimation of how much the actual prototype could cost, and including parts and labor, it comes up to about $2,500. Now, with all that, I give you Joel, who will present our conclusions in this project.
Thank you, Mark. So, in conclusion, we were able to design a device that will mitigate the wind. Will be able to generate electric power at different wind speeds, and will reduce the. We're predicting a reduction of the uplift effect of almost an 80% at 10 meters per second. Then we were able, all through this study, to correlate our data that we obtained from the experiment with ANSYS simulations. And then we are, since this is a new study, new type of device, we are proposing to continue the investigation of this device based on the three-blade twisted sabonium, which is the result that we obtained. And for that, we have a list of recommendations. And from here, we want to point out three. First, wind speeds. We were limited by a wind tunnel. One of the objectives of the project was to mitigate the wind during a hurricane, but we were limited by our wind tunnel. So next study will definitely be with wind speed of until at least 30 meters per second, which is category 1 hurricane. Then study with biphasic flow, so we can take into account the rain that will probably come with those strong winds and see how that's going to affect our device or the roof or the boundary layer. And then a 3D analysis for the simulations in order to better correlate results. Now, I will put Junior to conclude the presentation.
Thank you. We cannot conclude before we say thank you to our advisor, Dr. Andres Remante. Thank you very much to a PhD student, Javier Valencia. Special thanks to a PE, Pelayo Calante, our sponsor. Thanks to Professor Sicarelli in the lab, very helpful. Dr. Suganov, Dr. Sekin, they help us with ANSYS, and also all these students, Paola, Sergio, Omar, and Ms. Rosillo. Thank you very much for all your help and support and your patience. Thank you. This concludes our presentation. We're open for questions.
Well, yeah, I'll go first so that you don't steal all my questions. This happened before. Okay. The system that you designed, was it designed for power generation or for hurricane protection? Or
It was designed for both, taking into account both, but our main priority was wind mitigation. Then once we had accomplished the wind mitigation, we covered that, then we start seeing the different type of design that we could get then the best power generation. The idea is a device that would be able to mitigate the wind in case of a catastrophe, but at the same time, during the whole year, it's going to have that extra value of generating power.
Okay. In your fluid model,
Yes.
what assumptions did you make for wind speed?
Constant wind speed.
Of what?
Of what?
Of what speed?
10 meters per second, which is approximately, with 10 and 8, with round two studies.
Okay.
The one you
Now,
see-
when you're sitting in a hurricane,
Yeah,
that, I'll use Hurricane Andrew as an example, this is the one I
Yeah.
remember. And, because I lived through it, and I saw the maps showing 168 miles an hour.
yes.
Would the turbulence or the pattern of the fluid model have changed if you're doing it at 22 miles an hour versus 168 miles an hour?
Definitely.
Okay,
Yeah.
and do you know the answer of how this would perform?
No, of course not. Of course not. The thing is, we were limited by our wind tunnel.
But this is your fluid model. You could have,
Yeah, but
you could have calibrated your fluid model with the wind tunnel speed, but demonstrated or presented to us a condition that proved that the high-speed condition would have been the same.
At those velocities, we're probably gonna need a different model than the one we use K epsilon two equation, realizable, and non-equilibrium wall functions. But at those velocities, we're probably gonna need to go a little bit deeper. And ANSYS, just to understand and to run that type of analysis, it took us almost 4 months. It's really complicated. We have help from a couple of professors, but that's a software that understand what you're doing. You have to understand each and every variable model and even the mesh. If you have just one mistake, then it's going to alter the entire result.
Okay.
So we use it. So we use it mostly to correlate our results from the experiment.
Okay. Let me ask the next question. In your wind tunnel model,
Yeah.
the scale of your turbine to your house, is the expectation that this system's going to be half the wall thickness of your house? Then how can you use that model to correlate the phenomena that you're going to see in a system that you're going to use for mitigation?
Quickly, everything we focused on this project was basically trying to prove the concept. This is a completely new approach that had never been done before. And what we did basically with this project, I think our main achievement was to prove that putting such kind of device in front of the house does mitigate the wind. Of course, there's many, many more things that need to be considered. That's why we have a big list. And I think that is one of those.
Yeah. The other aspect of that is the house, if we kept the house that size, and then we try to come up with a model, a scale, then at that size, I don't think we can predict exactly what is going to happen. It's really, really, really small. We have only 12% of the cross-sectional area, so we try to use these type of models, and assuming that another assumption was that even though the house is small, the behavior is not going to change that much if we take into account just the upper half of the house and at the beginning. And exactly in that zone, if we go back to the first slide when we see the uplift effect, it's exactly at the beginning of the roof, at the edge of the roof, when we have the most failure. The uplift effect is right there. Right there we have the minimum pressure and then a lift on pressure. So if we can predict that by putting a device, we can modify the boundary layer and therefore reducing or maintain the pressure all along the roof, then we can assume that we're reducing the uplift effect.
Okay, and then my very last question is that classically in hurricanes, you get tornadoes.
Yes.
On a house like this, how would you place these turbines in order to protect yourself from winds that aren't necessarily all coming from one direction?
We have,
I mean, that's a good question. I mean, we tried to do what we did it as a sensitivity study, and we tried to put the ideal boundary conditions in the experimental part and also the ANSYS part. The questions you're referring and you're asking is more related to what's going to happen in the real case, and not only because of the limitation that we mentioned before. We did thought about that, but it's very hard to predict what position, unless we had the opportunity maybe of the foundings to go and do it in a world of wind at a real scale, having the prototype, and built, and then just run that for 3 months or whatnot to give you the best answer and address that answer.
Yeah.
I don't know if that.
nonetheless,
Very nice.
the turbine is supposed to go all around the house, covering pretty much all the
That's it,
the
yeah.
angles, but we didn't have the foundings to study like with a 45-degree angle, like the cortical vortices and what's going to happen with a wind change in the wind direction. We couldn't cover that, and since we don't have a precedent that we can use as a reference.
In addition to what I said, we were interested in the separation, the flow separation within the boundary layer. And we proved here that we were able to take care of that issue. And we wish that we can, have everything to just give you the most accurate result from the real case.
Thank you.
All right, I have one, I guess, Dr. Basil, is that something?
Sure.
Okay. Based on your work, what kind of confidence do you have that you can make some valuable contributions from the results of your work to contribute to building codes? Because in the end, what you're doing needs to end up in the building code for those people who will not have the means to go through this kind of rigorous analysis so that we can protect buildings in the future. So how would this project to improve the building code?
To prove, I'm not sure I understand your question.
Well,
Building code.
excuse me.
How we want to modify the building codes?
What contributions could you make to the updating, upgrading of building codes to incorporate these kinds of features in future buildings?
That's a great question. We mentioned before about the LEED certification and that this project qualifies for 2 of those credits. I think this is a really great start for this. And we mentioned, I want to mention again, that this has never been done before. Nobody has ever studied something, a device such as the one we did in this project.
That's why it needs to get into the building code.
Exactly. And I think the very first step is what we did here, just try to prove the concept and do some analysis. And that is something that will come after. If further analysis, there's many things still that have to be studied. We have a big list of things. As we were studying this device, we realized that there's many more things that should be considered. But at some point, and in the future, given that this device is so helpful for wind mitigation and for power generation, obviously I think building codes will follow.
So I would suggest that you put that on your steps for future action.
Okay.
Yes.
Thank you.
Stop the video.
You guys have questions?
You mentioned that the best location was going to be at the, I got confused either at the bottom level or at the top?
No, top.
Okay. So how is it going to be mounted to the house or to
Yes,
the building?
that's a rough one, let's put it that way, because I'm not gonna tell you, we're not gonna like that we consider that, we stated in the report, meaning that we actually said that we need help from civil engineers and also people from architectural engineer, so we can come together as a team, reinforce the team, member, ways to do things, and basically that's something that we didn't analyze as a mechanical engineer. In order to get that done, you have to take into account all the mechanical components, stress analysis, and we list that, different steps that we suggest for someone else, to continue what we started. Yeah. But it's a lot of mechanical components that has to be considered.
Yeah. In addition to what my junior is saying, is since this has no precedent, and we try to define what the boundary of this project will, or what will cover, we try to focus in what change will do, like aerodynamic change, the boundary layer, the fluid mechanics part. Once we have that, that's our part of our conclusion, like saying, okay, we need to continue this and see how it's gonna retrofit. Is even one of the recommendations, retrofitting into the house. And of course, stress analysis, I can recommend, for example, from research, I tried to do it, but keep giving me errors. It's doing a couple study of structure, structural stresses with a load of fluid. So that will give you an idea if it's going to fail or not, but it really was too much for us. ANSYS are really complicated too.
It's mostly a time constraint.
Yeah, and computer.
That's why we put it in computer, of course.
Yeah.
The computers we couldn't run a 3D simulation, and that's why we put it in the recommendation for future studies.
Yeah.
I have 2 more questions.
Yes.
So you guys only tested with 8 and 10
Yes, we did a full study before.
Okay. So since there's not enough data to support, let's say, for hurricane type things, and let's say, theoretically speaking, if you were to put this on top of the building today, would it be easily removed? Would the user, whoever's using it, would you just have to
That
make
should
sure
come
that's part of
after.
it?
Yeah, that should come after. In order to place it in the building, we first need to have to select all the part, to create a full scale model, test it, and then we can say how it's going to retrofit into that building, since we were not able to cover that.
You have a product, right? But you have to also think about how, when you sell the product, how is the user?
Right now, we have a potential problem.
We thought about it. We just didn't have enough time to complete everything we got signed. Absolutely, we definitely thought about it. You can see in our recommendation.
Yeah.
Still got a long list.
Unfortunately, it was time constraint. There was a major constraint.
No, you're right. I mean, everything you're asking, we thought about it, we studied the report, due to a time constraint, due to a lot of factors. There's a lot of combinations, that work not necessarily in favor of this project. Such as, those considerations to address that, such as time, for instance. We focus in that part only.
Yeah.
I did not get a chance to read your report. This is why I'm asking.
Oh,
okay.
absolutely.
Yeah. So basically what they're saying is you have to limit the scope because of the time and
We
funds.
set ourselves at the beginning of the project, we had a very big scope. We wanted to do so many things. And as we went, we realized that there was so much more work that we thought. So we had to start cutting back on some of those aspects. And then we wrote everything on most of those in our recommendations, because this is an area that has so much potential, but this is just the very, very first step. There's so much more to do. There's so much more to do.
Can I throw one more thing
Yes,
out about
definitely.
scope?
Waiting for
All right,
it.
so we'll go one more with scope, right? So you're gonna have it on your poster. What about human and wildlife safety? So
Yes.
first slide's right near one of your
Yes,
slides, right?
yes.
This, anyway, we talked all about scope, so I
This,
I'm just throwing it
right
out.
here,
Yes,
it's right here.
Yeah, yeah, okay.
So
So you have a curtain
talk
that
about our
changes all of the
Yeah,
fluid dynamics.
exactly.
of
We
all of your
then have
So
to
anyway.
repeat the study because we can then redirect even the flow.
Absolutely.
You know how it is. In real life, it's just like that. You think something, and then you gotta face different obstacles, and then you just gotta,
And we decided
Get the best out of
to
that.
get really deep and get good results that might start a possible study instead of just bites of different topics.
All right, that's, oh, you got one?
Great report, well written, well formatted. Thank you.
Thank you.
Thank
All right,
you.
there you go.